All right, hello class, and welcome back to the fourth part of this lecture. So in this final part, we're actually going to do two things. We only have 7 slides, so I'm going to try and fit them both in. I could break this down into 2 parts really, but I don't think that's necessary. In this lecture, we've shown that systems, if they're dealt with correctly, can be treated similarly to just functions, just matrices. So, yeah, system G, right, with inputs and outputs U and Y, and we've shown that this system can be represented. Of course, it can be represented in state space form A, B, C, D, but it can also be represented as a transfer function. And then in the frequency domain, the action of this block is multiplication, similar to how a matrix multiplies vectors. But of course, here we're working with functions, and so it's a little bit more complicated. But at least in the frequency domain, it's not too much more complicated. You just multiply the transfer function by the input in the frequency domain. Now, before we get too excited about this, of course, it allows us to do lots of things which we couldn't do otherwise. So, for example, we can decompose these blocks into lots of other blocks, right? And sort of write down equations for each of the subblocks, and then try and reduce our block diagram to something similar. Something like that, which we'll talk about shortly. But again, we don't want to confuse the representation, and G is just another representation of that system, similar to how ABCD is. It's just as a representation which has more in the way of physical interpretation. So in the previous lecture, or previous part of this lecture, we showed that if this G is bounded on the imaginary axis, right, G of I omega is less than or equal to gamma for all omega, then the system norm, G, also satisfies a bound. Now it's the induced norm bound from the input space to the output space, L2 to L2. Right? And the interconnection, of course, is because this is, by definition, the H infinity norm of that system. Or I should say, the H infinity norm of that transfer function. So we say use the H infinity norm interchangeably for systems and for transfer functions. But really, rigorously, the H infinity norm only applies to the transfer function, and it's a signal norm, but it's equal to the induced L2 norm on the system, right? And then we allowed, through optimization, a connection between this norm, these two norms, and an optimization problem defined on ABCD. Right, those state space representation matrices. Right. So in this first part of this final part of the lecture, we are going to talk about some other interpretations of this transfer function, not just bounding it, but we'll also talk about the H2 norm of that transfer function. We've seen the H2 norm, right? The H2 norm of a signal anyway. And remember, H infinity norm is a signal norm anyway, so it makes sense that we could also define those on functions, on transfer functions. So remember, the H2 norm of a signal in the frequency domain is equal to the L2 norm of that signal in the time domain. Right. Now, for transfer functions, right, obviously, who cares what the L2 norm of the transfer function is in the time domain, because, right, what does the time domain interpretation of a transfer function even mean, right? So there's some limited utility, but we will show that there is some physical interpretation that we can add to this. So specifically, we talk about the positive real lemma first, right? And that's defines a notion of passivity, right? Inaction, if you will, a relationship between the input of the system and the output, and particularly that the input and the output of the system, when you take the inner product of those two, right, it's greater than or equal to 0, right? So if you have the input of the system, inner product with the output, that's greater than or equal to 0. Now, if we turn back a few slides, we can tell us something, maybe a physical interpretation of what that actually means. So remember any inner product, and this is in the time domain, right, can be interpreted, right, as an angle between these two vectors. To cosine theta. So what does this tell us about the angle, right? Well, it tells us that, remember what the cosine looks like. It looks like this. So that when this angle between the two, or when the inner product between the input and the output is positive, that means that the angle here is between negative 90 degrees and 90 degrees, right? So that your input in this weird looking vector space, it makes an acute angle, right, with the output. The input and the output make acute angles, right? So they don't go in opposite directions. So they're sort of both pushing the same way. Okay, so we can say something about what that interpretation is. And now that's the definition of passivity. And the relationship between passivity and properties of the transfer function, so this passivity is a property of the system property. And the transfer function itself, right, is actually relatively easy to state. And in fact, I think I've got it on the next slide, but I'll just repeat it here. That this passivity relationship holds if and only if essentially the g plus g star is greater than or equal to 0. So positive real lemma, right? That's the name, positive real. The positive real part of the transfer function, or the real part of the transfer function, is positive. Right? So positive real. So if the transfer function is positive real, it turns out that because the inner product in L2 is equivalent to the inner product in H2, the positive realness, the positivity of this transfer function, right? This inner product of U and U of S and G of S, U of S, right? This is the Laplace transform of the input-output. If G of S is positive real, then of course this is going to be positive as well. Now, okay, so we can relate another property of the transfer function to a property of the input-output system. So that's very nice. So that's not really a result. That's just sort of definitions. And then, of course, the idea here is that this can be related through an optimization problem to the system ABCD, the state space representation itself. And here, if you may recall, this is CSI minus A inverse B plus D. All right, and that's the transfer function. So this is another LMI which relates those two terms. This one I will not prove, but you can prove it if you like. It's actually follows in a similar manner to the KYP lemma, and actually you might even be able to interpret this as a special case of the KYP lemma. So that's one additional property of the transfer function related to the system, related through an optimization problem to the system matrices A, B, C, D. Another convenient point, which I didn't mention, right, is that you can also read this information off of the Bode plot, right? The phase between your inputs and outputs is represented in the Bode plot. Before we talked about the magnitude as the H infinity norm, here we're talking about passivity as the phase, right? Remember, the Bode plot is the phase of g of I omega and the magnitude of g of I omega as a function of frequency, right? And this maximum here was the H infinity norm. And now the passivity theorem says that this phase should stay between negative 90 degrees and 90 degrees. Right? So that's nice. So it means just basically your lead or lag of the system never strays more than 90 degrees from the nominal. So that's a nice interpretation. The second property of the system, which is related to properties of the transfer function, is the H2 norm. Now here, the interpretation as a property of the system is much, much more tenuous, but we can do certain things with it. We're not going to get into it now. We're actually going to put that off to lecture 11. So we'll come back to this, what this means physically in lecture 11. So we're not going to actually go into it right now. So purely at this point, right, we're saying that p hat or g hat from before last lecture are representations, transfer function representations of the system. And they're functions, and so we can treat them as functions, treat them as signals. And before, we decided to bound the norm of those transfer functions, right? H infinity norm. Right? But remember, we had that other signal norm, H2, which was the integral of that signal along the imaginary axis. Right? Where did that? So okay, it makes sense that we could write a signal norm in the H infinity norm on the transfer function, and so it also makes sense that we can write the H2 norm of this transfer function. Now, I don't want to read too much into the H2 norm of a transfer function, however, because, again, it is a norm on the representation, right? So it measures the size, the square integral of the representation. And so interpreting that as a property of the system is actually rather difficult. And yet, we will get into lecture 11 where there's connections with LQR and filtering and so forth. So it will have its use. So I don't want to completely dismiss it at this point. But there's no obvious interpretation in terms of the properties of the transform. The H2 norm is very similar to, for matrices, the Frobenius norm, where you just took the square norm of all the elements of the matrix. Now, does the Frobenius norm of a matrix actually tell you anything about what the matrix does? Well, not much, but we can still define it. And importantly, of course, in lecture 11, we'll come back and show that it has some value. But at this point, we're not going to talk about it, except to say that this signal norm on the transfer function can be converted to an optimization problem, right, on the system ABCD. So there's limitations to this. First of all, there's no D, right? And why is there no D? Why do we not allow a D here? We didn't write it in our full generality, right? A, B, C, D. We didn't write it in that way because we don't allow the D's. And why don't we allow the D's? Why don't we allow a direct feed-through term? I mean, if we're thinking of block diagrams, it's obvious, well, if we just have it a matrix and matrix multiplication, well, that would be certainly well posed. Y equals D, y of t equals D u of t. Well, the reason is if you take the transfer function of D, well, the transfer function of D is D, right? It's just a matrix. But then what is the square integral of D? Well, that is, well, let's take a look at it. It's the integral along the imaginary axis of g of I omega, but of course there's no omega, so it's just integral of d, really d transpose d, d omega, 0 to infinity. And of course, you integrate a constant from 0 to infinity, and the result is, of course, infinity, right? So the H2 norm of a matrix is infinity. So now you sort of get the idea of why we're a little bit skeptical of the H2 norm in general, because, well, it can't even, finite H2 norm doesn't even allow us to represent matrices, and matrices seem to be a fairly well-posed kind of system. And so if it doesn't allow for matrices, well, we're going to have some problems going forward. Furthermore, we also require that the A is Hurwitz, right, in order for this theorem to work. Right. If A is not Hurwitz, you can actually still, there are certain cases where you can still have a square integral, which is well defined, but this relationship doesn't hold, right? So we also require A to be Hurwitz, and of course that's going to imply that a priori we already have a finite H infinity norm. Right. Given that, it can, however, be related to a LMI, right? So this is an LMI, and if this LMI is satisfied, so from positive x, it implies that the H2 norm of the system is finite, and it furthermore implies that the system is Hurwitz as well. So you get both of those properties. And you can see the Hurwitz nature, right? You just move B to the other side, and we have the stability. And this is actually, remember, just the LMI for the controllability gramian, with a little bit extra added onto it for the output. Right. And because, right, it does connect this idea of the controllability gramian to the system transfer function representation properties, it's worth going through very briefly the proof of this, because it actually uses the properties that we've already talked about. Okay, so what is what's the proof? So the proof is actually relatively straightforward. If we suppose that A is Hurwitz, and this is satisfied, then we can define the controllability gramian, which we've already seen and learned to like. And it turns out that actually is a solution to the system, to the optimization problem. And how do we show that? Well, first of all, we show that by taking the Laplace transform of basically the controllability gramian. So we just take the part that depends on time specifically. Well, let's focus on that for a moment. So what is the Laplace transform of e to the at? So remember, if we had a sort of an open loop solution, right, you have x of t equals e to the a t x naught, right? So what's the Laplace transform of that whole thing? Not a lambda. So let's find out. Remember, we could just put x naught as a constant outside of it, so we don't need to worry about that. So let's apply that. The definition of Laplace transform, here it is, right? We're taking the inner product with these test functions. And then integrating over time. So let's expand that out. Now we put the si minus a in there. And we have the integral of this, but what is the integral of this? Well, if we multiply the numerator and the denominator by si minus a, right? Well, if we just focus on this part, right, that's the derivative of the exponential, right? So we can actually, so we'll pull this part out of the integral, and then so we have the integral of a derivative, and so we can do we can just take the value of the exponential at its limit points, t equals 0 and t equals actually positive infinity in this case. And so we look at this bit, and well, at t equals infinity, right, by assumption that a is Hurwitz, right, these negative signs cancel out, e to the at goes to 0, right, so that term goes to 0. And then we're left with the 0 term. Well, this is all 0, and so e to the 0 is just identity. And so the only thing we have left is this sort of matrix pencil. And so then we can just add c and b to the left and right side of it because they're constant, and we get that the Laplace transform of this whole term here, ce to the atb, is just our matrix pencil that we started out with, g of s. Yep. Notice, however, that assumption on Hurwitzness, right? This relationship doesn't work unless the system is known to be stable a priori, in that it has a finite h infinity norm based on that. So then we then go to the h2 norm of the matrix pencil, or the transfer function, g hat of s. We expand out the definition. Well, it's the square integral of that transfer function, so we write out the square integral. We have the trace here because that's part of the definition as well. When we have before we had vector valued functions, right? So here we have matrix valued functions, so we have to add the trace, because now we're dealing with matrix valued functions. Okay. So we have the trace of g of s star g of s. And one nice thing about the trace, right, is it has this linearity property, which allows us to swap these two terms. And so we can get the trace of actually g hat of s star. Okay. Next, okay, well, let's look at that. We have the square integral of this transfer function, a signal in the Laplace domain, frequency domain. Well, Plancherol's theorem tells us that the H2 norm of a signal in the Laplace domain is equal to the L2 norm of the g of t, if whatever that would happen to be. Remember, it doesn't have a physical interpretation. The norm of g of t in the L2 norm, right? So this is g star of s in the H2 norm, oops, not L2, H2, is equal to the norm of g in the L2 norm. And what is that? Well, we just figured out what the Laplace transform of these two terms in, so now we just plug them in, right? And then we get this term here, and so we just bring the integral inside, move the c outside, and so what is this core? Well, that's nothing more than the controllability Gramian. And so the H2 norm then, through this proof, we've shown is precisely equal to the trace of C times the controllability gradient times C transpose. So another way we can relate the H2 norm to this positive matrix through a controllability gradient, which of course acts like a Lyapunov function. Right. And of course the gradient is positive, and we just proved this, and so we conclude that if the LMI is satisfied, then this is true. Actually, this proof also works for the observability gradient as well, right? Right. So this is the observability gradient. Remember, that's a function of C and A, right? And so we just add the B here term to get the output property, or the input properties. So this tells us about the output, and now we add a B to get us the input properties. Either case, right, they're both equal to the H2 norm. Now I've got a little bit here about making the inequalities strict, which I won't get into because remember this was these were non-strict inequalities for the gramians, and here we can just make them a little bit strict by adding this positivity term inside this integral. So thus we get, right, that if the H2 norm is satisfied by just construction of the gramian, we can prove that it satisfies this inequality, right, and vice versa. So again, relating system properties indirectly through the gramians, though how you interpret that at this point is a little bit up in the air. So gramians will, as a substitute for system properties, to a function of the representation in the H2 norm to an LMI in the state space representation A, B, C, D. So that gives us three results, three theorems, which relate properties of this transfer function to properties sort of the system, although in the last case we're dodging it a little bit there, and to through an optimization problem, properties of the matrices themselves. Next, and here I'm not going to break the lecture because it's really rather short. Next, we show what happens now equipped with all this mathematical machinery. We show what happens when you've created the framework which allows you to treat systems as you would treat matrices, right? It allows us to have an algebraic framework, something where multiplication makes sense in the context of composition. When you have an algebra, right, you can do algebraic manipulations of these systems because you can, assuming they're all in H infinity, they act similarly to matrices. And so now we'll give two quick results on properties of these transfer functions, of the block diagram simplifications that we would like to make. So for example, if we link up two blocks in negative feedback, right? So I put negative feedback on both just because, to be perfectly general, I don't know which is the controller and which is the plant, although obviously this is probably the plant, but we don't necessarily know that. So I put feedback on both of them, but we can probably ignore this one for the most part. Although remember, noise comes in here. Noise would typically come in here, and this would be a disturbance if you're thinking input-output properties. In any case, what this allows us to do then is write down equations, algebraic equations, for inputs and outputs where these things are functions, right? And these are systems, right? So we can write down equations, two equations, First one for y1 equals g times u minus y2. Right? That's the first equation. And the second is an expression for y2, which of course gets then plugged into here, which is k times u2 minus y1. Right? So we have two equations. We can go further. We can actually simplify, or we can write these in sort of matrix form, concatenating our signals together. Both our y's there and both our u's here. Right? Bigger y and bigger u. And then write those two equations down in sort of matrix format. Right? So y1, right, goes there. Negative g goes there. G goes there, and so forth. Right? So we can write these down as matrices. So we can also do manipulations because, right, we can treat these things as matrices. So for example, we can move, so there's an identity matrix here, I. We can move this term to the left-hand side, and then we get just two terms, two matrices, right? This is the same matrix, and this one is where we combine these two terms on the left-hand side. And so now we can go even further. We can say, well, y1, y2 is equal to this matrix inverted, right? We can take the inverse of this matrix on both sides. Take the inverse, that's minus 1, times g naught 0 k u1 u2. And so we can find an explicit expression for the outputs as a function of the inputs, right? We can simplify this block diagram using block diagram algebra. And a block diagram algebra only works if you have an algebra, obviously. And then furthermore, we can take results which were derived from matrices, like the matrix inversion lemma or formula, and apply them to these systems. So for example, the matrix inversion formula gives you an explicit expression for the inverse of a 2x2 matrix, which we have here. We're trying to invert that thing. 2x2 matrix in terms of all of these blocks, right? So these are just the elements of the original system. Actually, we're going to focus, I believe, on this representation here, where Q1 and Q2, right, are defined as inverses on these particular blocks, right? Of course, A22 here, right? We can plug these in for, let's see, Q1 here. And then, of course, don't forget we have to multiply G. That's why that's showing up there as well. So we have this term, and this term, and then we get the GKs there, and there for multiplication here. So we can find then an explicit expression for the output as a function of the input, right? Very important expression. For the output as a function of input. So it seems like, right, with this representation, then we are done, right? We know, given our inputs, what's our outputs. But of course, we're not quite done because, right, not all matrices are invertible, and likewise, not all operators are invertible. So in particular, we're interested in whether this operator is invertible or whether this operator is invertible. Although they're similar, right, because, right, it's just kg versus gk, right? So not much difference there. Right, so how do we know if this is invertible? And what do we even mean by invertible? Well, invertible means in this algebra that the inverse is an element of the algebra. And what is our algebra? Well, it's H infinity. Right? Is I minus kg inverse an element of H infinity? And so that, it turns out, is what we're trying to prove, right? Because if this is an element, this whole thing is an element of H infinity, and then the relationship between inputs and outputs is stable. And furthermore, we can find a norm on it, right? We can find just the norm of this big thing. However, of course, the question of whether I minus kg or I minus gk is invertible is a big one, right? That is the question, in fact. Fortunately, however, we can, because we're working with this algebraic representation, we're multiplication, convergence, norms, everything is well defined, in a similar manner as for matrices, we can take very simple results from analysis and extend them to these types of systems. So in particular, well, what are we trying to prove the inverse of? We're trying to prove that I minus gk, right, is in H infinity. It's well posed. It's not infinite, right? Specifically, we can say that we want that the H infinity norm of that to be less than infinity, right? We don't want that to go to infinity. Well, how do we take, if these were scalars, right, in your standard algebra, how would we determine whether this thing converges? Well, if you remember the power series expansion, right, we know that if this is just R, right, then what is that inverse? Well, it's just the summation from k equals 0 to infinity of R to the k, right? And we know that this converges if R is less than 1. In fact, if and only if, well, no, I wouldn't say if and only if. It converges if less than 1. If R is less than 1. And then, well, does this hold for systems? Well, it turns out because we defined our norms rigorously and we defined convergence and we have a Hilbert space, that Banach space, we have the convergence in norms implies convergence to an element of that space. And so the answer is yes. This works for systems as well. Right? If the H infinity norm of gk is less than 1, then this inverse exists and the system is well posed. Right? So, okay, that's pretty interesting. And then, so what are the conditions that we can do here? Well, if the norm of g times the norm of k is less than or equal to or strictly less than 1, then we have stability. We can show the stability. And that's all there is to the Small-Gain Theorem. That's what the Small-Gain Theorem is. So if the gain of g times the gain of k is less than 1, that implies stability. And this condition is called small gain. Right. So, okay, well, that's pretty impressive. And it actually took almost no work, right? Because we have this mathematical machinery and things which apply to matrices and apply to scalars work if everything is in H infinity. Right? So, well, what else can we do? Well, actually, here, before I go to the next result, which is the final result, and it's the final slide in this lecture, I do mention, right, that of course this small gain thing doesn't work with H2, right? If the H2 norm of each subsystem is less than 1, does that imply the closed loop system is less than 1? Well, it's not obvious that it does, right? Because the H2 norm does not form an algebra. We can't do block diagram simplification with finite H2 norm. We need H infinity norm. And so the answer is no. H2 norm does not work for these small gain purposes. And finally, right, we gave two conditions, right? We had H2, we had H infinity, and we had passivity, or positive realness. So passivity is more of a system description, system property description, and positive realness, positive real, is more of a description of the transfer function properties. But they're synonymous. So we had a small gain for H infinity. We have nothing for H2 at this point. And now we're going to get something for passivity. Right? So there's this, passivity was a big deal back in the 70s, where they were connecting lots and lots and lots of subcomponents of these circuit boards together, and they wanted to make sure the whole thing didn't blow up. Well, it turns out small gain wasn't entirely helpful, because if you connect two elements with small gain, yes, okay, in negative feedback, the result is stable, but it doesn't also have small gain. So that was a problem, because then if you add another component, well, you need the sum of all of the components to have small gain. That was just not realistic. So there was another notion introduced. So suppose we had like one component interconnected with another component, which is then interconnected with another component, which is then interconnected with another component, and so on and so forth, right? And right, if you have small gain, right, you really need all of these components. Well, it's just hard to interpret, right? And so an alternative condition that people came up with was this passivity, right? So if G and K are passive or positive real, right, then the interconnection of G and K will A, be stable, right? That's a requirement for everything we do. And furthermore, more importantly, it will also be passive, right? So that's the passivity theorem, right? Which relates either, if you prefer, the properties of the system, the passivity properties of the system, that the angle between the input and the output is less than 90 degrees. Or if you're looking at the Bode plot, that the phase is within plus or minus 90 degrees. Right. Then, if you interconnect these two systems, and well, there's a little bit of technical results. So first of all, for this result, this is from Desor and Fidisagar. We'll block off the 2, right? So ignore 2, because we're just going to focus on this one term, right? So it's the map from U1 to Y1, right? So in this case, we only need G to be passive. We need actually, well, the negative K, right, because it's negative feedback, to be strictly passive, right? So negative K to be strictly passive, which basically means, if you want the transfer function interpretation, G of S plus G of S star is greater than some positive constant, right? Although actually we're talking about K here, right? K is strictly passive. Then this interconnection is an element of H infinity and is passive. Right? And so that means, of course, that U I minus GK inverse GU is greater than or equal to 0. Right? So because now this interconnection is passive, you can add additional things, and if they're all passive negative feedback interconnections, the whole circuit basically is stable. Right? And so that's was really the use of this thing back in the 70s, and it's still useful today. Right? Now for the other 4 maps, right, of course they're just generalizations, because you can just swap G and K, and then you swap the conditions, right? K has to be passive, right, if you're looking at this interconnection, right? And of course, the only important pieces of information are these 2, right, because you just put G, G's already stable, so you don't have to worry about G, right? Right. So this gives us stability of both of these 2 maps. And then if we swapped the G and the K in these conditions, we get the stability of these 2 maps. Right? So already you see the importance of the algebraic nature of these elements, right? The importance of treating these system properties not in terms of the transfer function per se, but in terms of what it means for the composition of these blocks. We don't have block diagram algebra without H infinity. It just doesn't exist, right? So keep that in mind, right? When you're interpreting block diagrams, right? That everything needs to have finite H infinity norm, or block diagram algebra just doesn't make sense. In fact, the purpose of the block diagram algebra in 99% of the cases is just to prove that the whole thing has finite H infinity norm. Okay, so this is sort of the analysis introduction, setting the stage. It's probably the most important lecture in this sort of 5-series section of lectures. In the next one, we'll talk about setting the stage for optimal control. Sort of defining inputs and outputs and making everything rigorous and closing the loop. And it'll actually hopefully take significantly less time. This lecture took quite a bit of time. And hopefully the remaining lectures will not take quite so much. We'll move a little bit faster. But this is, again, right, the concepts from this lecture are probably the most important for this series, without which, right, they're necessary for the rest of the lectures. So with that, I will stop recording and move on at some point to the remaining lecture 8, this next one.